Hello. So we are finishing up 7-2 notes today. And what we're covering in our 7-2 notes are two separate ideas of comparisons. So there's this idea of mutually exclusive and non-mutually exclusive. They don't really have like a good name for non-mutually exclusive. So those are like one comparison and contrast of events that could happen. And then there's also this idea of independent versus dependent. And they're actually two separate ideas that get mixed together quite a bit. So I just want that to be on your radar as we start to go through and learn these, that these are two separate ideas that are approached in different ways in probability, and the definitions of them tend to get mixed up. So try and remember to keep the ideas of them separate, and I'll give you some hints of like how I like to visualize it to keep them separate in my mind. Okay, so with that, mutually exclusive. So we're going to consider the following problem. If you draw a card from a 52 card deck, what is the probability that you draw a king or a heart? So we've talked about decks of cards. We know that there's a total of 52. We know that there's 4 suits. We know that there's 13 cards per suit, and that 3 of them are face cards. There's an ace, right? There's lots of things that we know. So if we're talking about this idea of the probability of a king, so if we want to know what's the probability that we're going to pull a king from a 52 card deck, there's 4 options. We've got 4 out of a total of 52. But it could either be those 4 cards or any other heart that we pull. So there's a total of a fourth of the deck is 52, is hearts, and out of 52, a fourth of 52 is 13. So it could be 4 cards that we pull out, or the 13 heart cards would also be under this probability. So it could be those 4 or the 13 that are hearts. There is a catch with this, is that there is one card that is both a king and a heart. And under the 4 divided by 52, the 4 out of 52, we've counted that heart king. But also in the 13 out of 52, we have also counted that king that is a heart. So we've counted it twice, and so you need to just make sure to subtract out one of them. So then what you do is you subtract out the one card that is both a king and a heart. So these are all the total number of cards that you could pull in the deck that fit those parameters, and how we talk about that is adding them together. Okay, so then 4 plus 13, 17 minus 1 is 16 out of 52. We could simplify, we don't have to simplify that down. But since there is this idea of an intersection between this or that, we call this not mutually exclusive. Since there is an overlap of them, this is a non-example of mutual exclusivity. So we'll go in here and write down a note to ourselves that this is because of this guy right here, this 1 out of 52 that is both of them. That means that this is not mutually exclusive. And how we calculated it is we calculated the probability that it was a king, and then we added in the probability that it was a heart, and then we subtracted out the probability that it was both a king and a heart. And this gave us the probability that it was a king or a heart. Because if we wanted the probability that it was both a king and a heart, it would only be one card, as we see in our subtraction later on. So that would be only 1 out of 52. 1 out of 52. So the probability it's a king or a heart is this formula. It's called the addition rule, and we use it when we're talking about something or something. Probability of a or B. And remember, with our set notation, or is this bridge. if we remember all the way back to when we started talking about this, this is your intersection between the two sets of A and B. The intersection, I like to think of this symbol, which is like an upside down U almost, as a bridge that's connecting A and B. So the thing that is the same between the two of them. So this or, no, I totally lied. This or this is this idea that we have any of those things that can go into this probability. So this is the union. Sorry, this is the union. This or this would be the union of anything. We could have this or we could have this, all of them together. And it is the probability of A plus the probability of B, and then minus the probability that those two things have in common. And this is A and B. The one thing that they both share is going to be subtracted out. Look, sounds like somebody just had a car crash outside. Look for the word or. That is going to be your key that you need to use the addition rule. Okay, let's practice. Paulina chooses an integer between 1 and 1,000. Determine the probability that is a multiple of 4 or 5. So writing out our ideas before we get started. Probability of 4 or 5 is going to be the probability of 4 plus the probability of 5 minus the probability of both 4 and 5. So if I were to just quickly calculate how many multiples of 4 are in 1,000, all you have to do is divide 1,000 by 4. So the probability of 4 is equal to 1,000 divided by 4. There are 250 numbers between 1 and 1,000 that are divisible by 4. And then the probability of 5, we would do 1,000 divided by 5, which is 200. If something is a multiple of 4 and 5, it's actually a multiple of 4 times 5. So it's a multiple of 20. So the probability of 4 and 5 is actually equal to the probability of 20. So that's going to be 1,000 divided by 20, which is 50. So we have that, well, so this is technically not probability because we don't have the division out of there. This is just events of 4 and events of 5. So to make this technically correct, we're going to go in here and divide out of the total numbers possible. So plugging these numbers into our formula, the probability of 4 or 5 is equal to 250 over 1,000 plus 200 over 1,000 minus 50 over 1,000, which is equal to 400 over 1,000, and we can simplify that fraction down to 2/5. So it's a 40% probability or 2/5 probability that the integer chosen at random is going to be either a multiple of 4 or a multiple of 5. Okay. In a statistics class, there are 18 juniors and 10 seniors. 6 of the seniors are females and 12 of the juniors are males. If a student is selected at random, find the probability of selecting the following. So what I like to do for these types of problems, this is a problem that is an experimental probability, right? Not a theoretical one, where the one before, it was just like, there are all of the options available to you and find the probability that these are chosen at random. Here, there's not like a half or 50% chance that it's female or male because we've actually counted the males. So we're taking from a certain sample set that's already been counted. So it's empirical or experimental probability, going back to the beginning of our notes. So I'm gonna turn this experimental probability into a table real quick. So we've got juniors and seniors, and then males and females. And there's no overlap here, right? There's not really a possibility for you to be both male or female, and there's not a possibility for you to be both junior or senior. So going through, it says that there are 10 juniors, so I'm going to write that down here as a total. 18 juniors, and then 10 seniors. It says 6 of the seniors are females. So if I go in here and write down 6 for seniors that are females, then the remaining 4 seniors must be male. And then it says that 12 of the juniors are males. So then if 12 out of the 18 juniors are males, then that means that there are 6 females that are juniors. So we can go in here and make totals of males and females as well. And so we've got our totals as well as our distribution of our experimental probability that we've already calculated. So then now we have this sample set, and we use this sample set to make the probabilities. So it says a junior or a female. So this is going to be our addition rule because of the word or. So, oops, I'm going to zoom in here. I've got my probabilities already written down, so I don't have to zoom back in and out. So a probability of a junior or a female is going to be equal to the probability of a junior plus the probability of a female minus the probability of a junior and a female, which there are some of those. So then the probability that there is a junior, there are a total of 18 juniors out of the total of 18 plus 10, or 12 plus 16 gives us the same. So adding up females and males or adding up juniors and seniors is going to give us the same number. It's a total of 28 students in this statistics class. And then the total of females is 12. And then the probability or the number of students that are both juniors and females are 6. So we've counted those 6 females twice. So we need to take out the double occurrence of them. And so we're subtracting out 6 over 28. So this is not a mutually exclusive event. So then that's going to be 24 over 28, which is simplified down to 6 over 7. I'm sure some of you are going to send me a message, and the answer is it doesn't matter about simplification of your fractions. I won't mark you down on whether or not you simplify your fraction.